Let's move on to Fourier Transforms. This is section 5.7. This is an application of a lot of the more abstract stuff we've been talking about until now. This is quite an important application, and it's not so easy, so I suggest you set aside some time to learn this stuff. And in particular, I strongly recommend you read this section in the book because it's quite long, and I'm not going to have time to cover all of the details. And as I say, this is quite an important application of linear algebra. So let me give a sort of brief introduction to the idea here. So the idea is we're studying function f of t, which I'm thinking of as being some sort of signal, for example, an audio signal. And I want to store f of t in a computer. And, well, the idea is to decompose it into a bunch of sine waves of different frequency, of various frequencies. So, for example, it might just be a sine wave itself with a given frequency, or it could be built up out of several frequencies, or maybe infinitely many different frequencies, and that's what the Fourier transform does for you. And since we're talking about, I talked about this about a week or so ago, since we're talking about spaces of functions, this really has to do with an infinite dimensional vector space. Vector space. And so it's a little bit outside the kinds of things that we've been talking about, but we're going to make it finite, and in practice it's finite because you only sample the function at a finite number of points. So I assume you know what I mean by that, which is that you only save the value of the function at some equally spaced collection of points. And on the other hand, what you try and do is you try and write f of t, or approximate f of t, in terms of a finite number of periodic functions. That is to say, functions of the form cosine omega t, where omega, or various omega it's, where you have some omega 1, omega 2, up to omega n, some finite number of frequencies. And, well, that's how you do that is the subject of the finite Fourier transform. And the setting is really finite dimensional vector spaces. So we can really talk about it in the language that we've been using so far. And so let's go on and say that a little more carefully. All right, so let's set up a little bit of terminology and such. I'm going to be talking about functions f of x, and as in the book, I'm going to use x instead of t, but you might want to think of x as being the time variable. And it's on we're on some finite interval, and it's convenient to normalize that interval to be 0 to 2 pi. So that is to say, x is a real variable running from 0 to 2 pi. And this f of x is either going to be complex or real, depending. I'm going to pass back and forth a little bit between these two, and you'll see why. And I choose some large number n, and I break this interval up into n equally spaced parts, and I label them x0, x1, x2, up to xn minus 1. And then associated to this function, a given function f, is its value vector f of x, which is to say this vector f of x0, f of x1, up to f of x n minus 1, And this is either in Cn or Rn, depending on whether f is a real or complex valued function. And this is all I know about f. This is the information that I store in the computer. And what I want to be able to do is, to as great extent as possible, I want to recover f from this value vector. That's basically the idea. And, well, f is a function, and I've only stored a finite number of values of it, so I obviously can't completely recover f from this. So there's some... It's not possible to completely do this, to completely recover f, of course, because if two functions might not be equal, but if they're equal at these points, then they'll have the same vectors. So, for example, suppose I looked at the function f of x is just a constant function, and suppose I looked at the function g of x is the function e to the I n x. Well, what is the vectors for these guys? Well, f is just the constant vector 1, of course. And what is g? Well, g is going to involve, I need to know what g of xj is. So I need to compute e to the I n xj. So this is g of xj. And what is xj? Well, if you think about it, xj, where should I put it? Xj is simply 2 pi j over n, because this interval right here is 2 pi over n, and then there's, you just keep taking multiples of that, and so xj is 2 pi j over n. And so what is g of xj? It's e to the I n 2 pi j over n, which is to say e to the 2 pi j, the 2 pi I j, excuse me, the n's cancel, and that gives you cosine 2 pi j plus sine 2 pi j, and of course that's 1. So this vector, the vector for g, is the same. And, well, this complex valued function, this is a periodic wave of frequency n. Now it's complex valued, so it's a little bit hard to picture that. But if you take the real part of it, you're getting cosine 2 pi n xj. Where should I write that down? The real part of g is equal to cosine of 2 pi n x, and that's a periodic function with period n, and we're sampling it at these points, and we're always getting 1. So the moral of the story is that this sampling at n points, it's unable to distinguish a signal of frequency n. But if you had a signal of lower frequency, then it can handle that. So you need to choose n large enough for the purpose at hand. Okay, so here's what we do. We have this function f of x for x between 0 and 2 pi, and we've picked this large number n. And the idea is that we want to write f as best we can, approximating it, by a function of the following form. I want to take a constant function plus c1 e to the ix plus c2 e to the 2ix plus dot 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 c n minus 1 e to the I n minus 1 times x. That's the basic idea. And so the point is that e to the I kx is equal to cosine kx plus I sine kx. And so if you take the real part of f, what you're getting is you can replace each of these things with ck cosine kx and so on. And so this is a sine. It's a periodic function with period 2 pi over k, and this is approximating the function by a bunch of, well, down here approximating this real function is a bunch of periodic functions of various periods or frequencies. And as I said, we're going to go back and forth between real and complex valued functions. It's quite a bit easier to think about this complex function, and you're trying to write it as a finite linear combination of exponentials. And complex exponentials are mathematically much easier to work with than sines and cosines. And so, well, basically what we're saying is we're going to, from f, we want to get these numbers c0, c1, up to cn minus 1. And this is the data which we're going to store, which is going to be giving me an approximation to the function. And what I'm going to say is to make this a little bit more precise. What I do is I let p of x be this expansion c0 plus c1 I to the x plus and so on, and I introduce the terminology f tilde p. And by that, I mean that f of xj is equal to p of xj for all j's running up to n minus 1. So here I said f of x is approximately this function. Well, more precisely what I'm saying is that it's equal to this function on all of the points that you're measuring. You can't ask any more than that because we're just measuring the value of the function at this finite number of points. So I want to find these c's so that this function and the given function are equal on these points. So here's what we're doing. We're given our function f of x, and we want it to have this relation with p of x, which is this finite sum of exponentials. And this relation here, this funny symbol, is exactly that these two functions have the same values at all of these points. And I want to get a vector identity out of this. Well, you have this vector f of x, which is f of x0 up to f of x n minus 1. And for each of these exponentials, e to the I kx, you get a similar vector, which is omega k, which is the values of this function at these points, which is to say e to the I k x0, e to the I k x1, up to e to the I k x n minus 1. And if you evaluate the right hand side, if you look at this vector p is where you evaluate this function at all of the xk's. Well, you see that p is going to simply be c0 omega 0. Let's put a vector over this to indicate it. And plus c1 omega 1 plus c n minus 1 omega n minus 1. Okay, so this is a bunch of vectors, complex vectors. Each of these guys here is in Cn. And so the identity that I'm looking for is that F is equal to this C0 W0 plus dot 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 Cn minus 1 omega n minus 1. I'm trying to solve this matrix, this vector equation for the C's, C0 up to Cn minus 1. So let's parse that for a moment. What am I saying? I'm given an n vector here, and I'm given a bunch of other n vectors, the omega 0 up through omega n minus 1. And I'm trying to write the given vector as a linear combination of these vectors on the right-hand side. That's clearly some kind of matrix equation. So I've copied over what we're trying to do. We're given a vector f. We want to write it as a linear combination of these omega i's, omega k's, where omega k is this vector. And I'm going to say this is a vector in some vector space V, which is to say this n-dimensional complex vector space. And I want to solve this for the CIs. Well, that you could obviously write down some giant matrix equation and solve it, but that would be computationally terrible. And the key point is to simplify it as follows. We define an inner product on V, and it's defined by VW is 1 over n times the summation VI WI bar, where VI and WI are the coordinates of V and W, running from 0 to n minus 1. And this is just a standard Hermitian inner product on Cn, scaled by 1 over n for convenience. And I suggest you go back to whatever section that was in the book about complex vector spaces and remind yourself about inner products on them. And the key point is that when you define an inner product on a complex vector space, you always put this bar on the second coordinate. And the key fact, which goes along with the key point, I guess, is the following: that the vectors omega 0 up to omega n are an orthonormal basis of V with respect to this inner product. So this is a tremendously powerful fact, because when you have an orthonormal basis, lots of computations become easier. So let's derive some consequences of this and then see why this is true. Okay, so how do we figure out these coefficients C, K? Well, we've seen this kind of thing before, and let me remind you how this works. When you have an orthonormal basis, if you're trying to figure out these coefficients, you take the inner product of both sides with the kth, with omega k, and what you get is C0 omega 0 omega k plus dot 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 ck omega k, and so on up to Cn minus 1 omega n minus 1 omega k. And by orthogonality, all of these terms are 0 except for the one with k. And by orthonormality, this number is 1, and the right-hand side is simply giving you ck. So you get a formula. Ck is simply the inner product of f with omega k. And, well, we did this in general before. I'm just reminding you how it works in this particular case. So that's a nice formula for CK. You don't need some big matrix or anything. It's just this thing, whatever it is. So let's write it out. What do you get? Well, by definition, this is 1 over n times the summation j running from 0 to n minus 1 of f of the jth guy times e to the I k x j bar. That's the omega k. That's the kth coordinate of this guy. And what is that equal to? This is 1 over n times the summation over j f of xj e to the minus I k x j. Okay, the bar just gives you the minus. And remember that xj is 2 pi j over n. And so we can write this as 1 over n summation over j f of xj e to the minus I k times xj, which is 2 pi j over n. And what is that? E to the minus I k da 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 da. So, well, it's convenient to pull out the jk from this thing. And let me just write it over here. What is e to the minus I k 2 pi j over n? It's this fixed number e to the minus 2 pi I over n to the k times j. And I'm going to write that as zeta sub n to the minus j times k, where, so let me just write this up here. The final formula is that ck is equal to summation over j f of xj times zeta to the minus j times k, where I guess I called it zeta n, where zeta n is this fixed complex number e to the 2 pi I over n. Okay, so let's just stare at this for a second. The way you calculate the kth coefficient is you sum up the values of f at the various xj's, and they're weighted by these complex numbers, zeta n to the j times k. The k is fixed, and the j is varying with the sum. So it's some kind of sum, and anyway, that's a nice concrete formula for ck. So let me summarize this. What we've been talking about is the finite, or sometimes called discrete, Fourier transform. And the setting is we're given this function f of x, where x is running from 0 to 2 pi. And we pick this large number n, and we break the interval up into n equal segments. And we define this function p of x is equal to c0 plus c1 e to the I x plus dot 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 cn minus 1 e to the I n minus 1 x, where ck is given by this formula 1 over n summation j running from 0 to n minus 1 zeta n to the minus k times j, where zeta n is equal to e to the 2 pi I over n. And we've seen that f and p satisfy this relationship. They have the same vectors. F of xj is equal to p of xj, which is to say, as far as sampling these points go, p is just as good as f. And the the finite Fourier transform is the map which takes this function f to this vector c0, c1 through cn minus 1. And the idea is that you've encoded this function with this other function p, which records the occurrence of the different frequencies in it. And the reverse map going from these back to f is the inverse finite Fourier transform. And, well, I'll say a little bit more about that in class. Let me just say one last thing before I wrap this up, which is this zeta n is what? Well, if you draw a picture of the circle, if you know how to draw a circle, let's try drawing a circle. There we go, that's a little better. This angle is 2 pi over n, and zeta n is an nth root of unity. This number zeta n, if you raise it to the nth power, you're getting 1. That's the meaning of it. And, well, I developed all of this theory based on the fact that these omega functions, vectors, excuse me, were orthonormal, which is to say this is equal to 1 or 0 if I is equal to j otherwise. And I didn't say why that's true, but I'll talk about that in class.